Today we're going to start looking at, direct, indirect joint variation, and we'll continue our studies this unit with some sequences and series. So this is really talking about patterns in general. And so the patterns we're looking at today, we can absolutely describe them by a pretty straightforward equation, but we do need to somehow relate how one term is changing versus any other term in that equation. And so we usually talk about how things are changing compared to one another in the variation problems with something called a constant of proportionality. And so that's the number that's going to relate those two variables or more variables together in an equation. And we usually show that in our equation by the letter K. So we don't use C for constant as much. We do have C in other values or other equations like standard form of quadratics and such. So we have a slightly different constant that we use for this one. Okay, the two main types of variations we're talking about today are direct and indirect. And they kind of go along with those vocabulary words, direct, straight on. Well, a direct variation basically means as one variable increases, the other increases. And so the other direction would work the same. As one decreases, the other decreases. They both kind of change the same. So as one variable increases, the other also increases. And so what this equation could look like, and what we would usually see this shown as, is y equals kx. And so again, there's that proportionality constant in there. And so as one increases, the other increases, and the description of how they change related to each other is that k value. Now, we could also see this in other setups, all depending on, what we've kind of solved out for. So you might see it as something like k equals x over y, which again, that's just solving the problem for k, or we might solve in terms of x, but usually we see it as y equals kx. And if we think about that, if that's a y equals equation, well, that's something that we could graph. And that doesn't look too far off from like y equals mx plus b. It's not missing that extra constant at the end, but it's otherwise in the same format. And so generally, if we were to graph this, we would have, a line. If we had a negative k value, what would that do to the line? It would just put it in the other direction. So it'd be going up to the left instead of up to the right. Now, indirect variation, again, goes kind of the opposite way. So as one variable increases, the other is going to go the opposite direction, so it's going to decrease. So as one increases, the other variable decreases. And again, the way we would usually see this is y equals k divided by x. And so if you think about what we've seen in previous functions, well, if we've seen something that looks like that value, like, y equals 1 over x, well, then graphing that out, we'd have the same kind of graph as those rational functions that we looked at a little while ago. So we'd have something like this, or again, if the k value was negative, the branches would be in the other two quadrants. And again, we could go through and look at the different versions where you solve this out. So for example, if you solve for the k, you might see this as k equals x times y. But again, usually those ones that have the boxes, that's how we're usually going to see these and how we're going to write them as we look at our problems today. Okay, two other types of variation. So we have joint and combined variation, and these are really just kind of riffs on the same direct or indirect variation. So joint variation is pretty much going to look like direct variation, but it's going to have more than one variable. So it's going to have two or more other variables, and an example of this would be like y equals k x z. So again, it looks very similar to the direct variation, just has an extra variable. And we could put anything in that we wanted for x. So for example, we could look at like y equals xz over 3, which really means our k value is dividing by 3, or it's 1/3. So again, both of those would be joint variation problems. And then we also have combined variation problems. So it's going to be a mix and match of different variations. So for example, we could have y equals k x over z. So notice the k is still in the numerator. We're kind of multiplying by the x, like direct variation, and dividing with the z, which is like our indirect variation. So let's just see a bunch of examples on this and see how we can solve these out. So first set of examples is really just how do we determine which one's which, make sure we can identify what kind of variation is happening. Okay, so in number 1, we have xy equals 12. Well, 12 is definitely a constant, so I would call that our k value. So if we kind of revamp this just to get one variable on the side, then we could probably solve that for our y, divide both sides by x, and now it looks exactly like an inverse variation. And again, I'm just trying to get it into that format that I'm a little bit more used to using and that I'm going to use a lot more in these examples. Okay, but number 2, a equals 8bh. Well, we have the 8 constant, and then we have 2 extra variables, b and h. We don't have any divisions going on, so this looks a lot more like our joint variation, kind of a couple direct variations together. And then we have number 3, y divided by x equals 31. And again, just to relate it to what we have in our patterns above, if I solve out for that y by multiplying both sides by x, again, this actually looks a little bit more like a direct variation. All right, so let's look at a few examples now where description's happening, and let's write an equation for them. So number 4, y varies jointly as w and x. So again, any time I see the word jointly, I think it's basically just direct variation. So that's going to look like y equals k times wx. Okay, number 5, y varies directly as the square of x. So when I see the square of x, again, I'm thinking x squared. And so y varies directly, everything's all multiplied. So y equals kx squared. Okay, number 6, y varies inversely as the cube of x. So cube of x means how are we going to write that x variable? Cube just means raised to the 3rd power, so that's really x cubed. And inversely means we're going to do a division. So y equals k divided by x cubed. And then number 7, y varies inversely as w and directly as the cube of x. So technically this is describing a combined variation because it's doing multiple variations, but we still need to describe each one so we know where those variables happen. So first one, y varies inversely as w. So I know that would look like y equals k over w. But then I also have cube of x. Well, same thing as the previous problem. I know that's going to be x cubed. Because it's directly, I know that's a multiplication and not a division, so he's going to go in the numerator of the equation. Alrighty, last few examples, just dealing with properties. 8 and 9, write a variation statement for each of the following models. So again, think about what's being multiplied, what's being divided. Any multiplication is going to be a direct or a joint variation. Anything that's dividing is going to involve an inverse. So if I divide it up, knowing that k is my constant of proportionality, then I can say for this one, g varies inverse, let's go, if we have multiple variables, the x or the p1 and the p2, yeah, that's going to be a joint variation. So varies jointly as p1 and p2. And then if we're dividing by the d, then that means he's an inverse. So inversely as d. Okay, in number 9, are we dividing by anything? So we don't have to worry about inverse variation. Everything is going to be a joint variation. So S varies jointly as, and I'm going to go ahead and keep B1 plus B2 in parentheses and H. And we could, if we wanted to, distribute that out, but the goal was just to write a description of what's going on rather than, worrying about simplifying our expression. So now let's look at what happens when we apply these. So let's solve some problems using these patterns. So when you solve a variation problem, obviously the first thing you want to do is make sure that you have the variation set up correctly, that you've got an equation that properly describes the situation. Then we want to make sure we know what that constant of variation is, which we're probably going to have to solve for it. And then we'll go ahead and then use that value to write a new equation and solve out the problem. So that means a lot of these problems, they're going to give you two sets of information. So one set will help you solve for the k value, and the other will solve for whatever variable it's asking for. So number 10, y varies directly as x. So there's our description of our equation. So we're going to start y varies directly as x, just like we have in the formula on the front page. Y equals -15 when x equals 5. So they're giving us enough information to solve for that k value. So let's just plug those in. So -15 equals k times 5, which means now I can solve for k. So divide both sides by 5. That tells me k equals -3. And so now I need to go through and rewrite my equation with that new k value in it. So this is going to turn into y equals -3x. And I'm going to use that then to solve for the final sentence, which says, find y when x equals 3. So all I need to do is plug in that value for x, solve for the y. So y equals -3 times 3, aka y equals 9. All right, number 11. So same thing, y varies inversely as x. Okay, there's my description of the equation. So y equals k over x. Second sentence, y equals -14 when x equals 12. So use those to solve for your k value. So y is -14, x is 12. We need to multiply both sides by 12 to solve for k. So 12 times a -14 gives me -168. Plug that back in. So my new formula is y equals -168 divided by k, x. And our last sentence, find x when y equals 21. So substitute in 21 for our y and solve for our x. So again, we have the x in the denominator of the equation. To simplify that out, let's multiply both sides by the x. Again, doesn't quite get it by itself, but it is going to get us to where we have a straightforward way to solve out for the x. So all we need now is to divide both sides by 21, and that will be our solution for x. So let's see here. So -168 divided by 21 gives me -8. Alrighty. Number 12, y varies jointly as x and z. So what's that closest to, direct or indirect? That's really just another direct problem. It just has two variables. So y equals k, x, z. So same scenario, plug in what you know, solve for the k, and then resolve for that last variable that they mentioned. So first sentence says, ooh, this one's twisted around a little bit. Find y when x equals 10 and z equals 5 if y equals 12 when z equals 8 and x equals 3. So they gave us the info in the second sentence. That's what we're going to plug in. So 12 equals k times x, which is 3, times z, which is 8. So 12 equals k times 24. So dividing both sides out, we're going to have that k equals 1/2 or 0.5. Either one would be fine. So again, substitute it in. So y equals 1/2 x z. And now I can go back to the first part of that second sentence. So find y when x equals 10 and z equals 5. So we plug in. So 1/2 times 10 times 5. Well, 10 times 5 is 50, and half of 50 is 25. Alrighty, number 13, go ahead and pause the video and try this one out. This is another y varies jointly as x and z. So same setup as number 12, just with different values. So go ahead, pause the video, try this out, and then restart, see how you did. Alrighty, so again, be careful that you are using the correct set of info to write your equation. I found that k was equal to -1. when I solved that out. So my new equation was y equals negative xz, plugging in the info that they gave us in the second equation. So find y when x equals 9 and z equals negative 5. Well, 9 times negative 5 gives me negative 45 times the negative that is out in front. We get y equals 45. Let's do a few word problems now. Alrighty, number 14, the number of oranges you can pack in a box varies inversely with the cube of the diameter of the oranges. So let's sift through that. So number of oranges, let's call that n, varies inversely, so I know I'm going to have a division. The cube of the diameter of the oranges, so let's call that d cubed for diameter cubed. So number of oranges varies inversely, so k divided by d cubed. Suppose a box holds 144 oranges averaging 2 inches in diameter. So that's what I'm going to plug in to figure out my k value. So number of oranges is 144 equals k over d cubed, so 2 cubed. Well, in other words, that means 144 equals k over 8. So multiply both sides by 8. So 144 times 8, that's a large multiplier, 1152. But those happen sometimes. So now the question is about how many oranges with 3-inch diameters would the box hold? So we need to figure out what the n is if diameter is 3. So our new equation is n equals 1152 divided by d cubed. And they actually gave us our diameter. So that's 3 inches. So 3 cubed, which is really 27. So 1152 divided by 27 gives us approximately, because I'm getting a decimal out on this one, so I'm getting 42.6 repeating, but you can't really have 2/3 of an orange. Otherwise, it's going to dry out. You're never going to get a bag of oranges at the grocery store that has one cut up unless it's prepped for service. So we're going to say 42 oranges. Same thing when we're dealing with any problems that ask like how many people, you can have a partial person because, you know, yeah, people are their own entity, a single person. So we always tend to round down in that case. Alrighty, number 15, the energy stored in a spring is directly proportional to the square of how much the spring is stretched. So directly proportional, pick out your variables, write your equation. So energy stored in a spring, let's call that E, directly proportional to the square of how much the spring is stretched. So we're going to look at the square of the stretch. So let's go S squared. So E equals KS squared. And if you take physics, that's probably not all that different from the equation that you could use in physics to think about forces with springs. So if 12 units of energy are stored when the spring is stretched to 2 centimeters, that will give us our K value. So 12 units of energy are stored when it's stretched to 2 centimeters. There we go. So actually, let's do this because they gave us the units and we didn't have to worry too much about the units in our previous problem, just keeping track. We were talking about number of oranges, but let's go ahead and write this in as 2 centimeters just to keep track of things. And so squaring 2 centimeters, we would get, let's see, and then 12 is units of energy, which again, I haven't taken physics in a very long time. So I know that there's, a specific unit of energy that we might use. I don't know what that is in this case. So let's just call that U for units. And then 2 centimeters cubed or squared would be 4 centimeters squared. And so our K value now becomes, divide both sides by that 4 centimeters squared. We're going to have 12 divided by 4 or 3 units per centimeters squared. So I actually do have units of measure to measure the force on here. Alrighty, substitute that in. So E equals 3 times S squared. And so again, we have that unit measure in there, and let's see what happens with that. So if I have anybody who's taking chemistry, I know this is one of the things that you need to pay attention to make sure all of your units match up. Same thing in physics. It helps you figure out that the values you're working with are going to give you the correct format of answer. So then our last sentence says, how many units of energy are stored when it is stretched to 6 centimeters? So plugging in 6 centimeters into squared. But again, we're going to have the same thing. If we do 6 centimeters squared, well, that's going to really come out to, let's put this guy in parentheses just to keep the units by themselves, 36 centimeters squared. And so if we're multiplying the 3 times the 36, well, that comes out to 108. But then let's take a look at the units. So in the first set of units, we have centimeters squared in the denominator, and we're multiplying it by centimeters squared. Multiply and divide, inverse operations. Those actually cancel each other out. So we're going to have 108 units of energy. And so our answer actually came out with the correct units for the type of answer it was looking for. Okay, last problem should look familiar. The volume of a pyramid varies jointly as its height and the area of its base. So let's write that equation out and see how it compares to what you may have used in geometry. So the volume of a pyramid, let's go volume, varies jointly as the height and the area of the base. And in geometry, we used a big B for that, so that's what I'm going to use here. And so we need to solve for the K value. A pyramid with a height of 12 feet and a base with area of 23 square feet has a volume of 92 cubic feet. So feet cubed. So let's plug those in and see where we're at. So volume is, let's see, 92 feet cubed equals, we don't know the K value yet. Our height is 12 feet. And our area of our base is 23 square feet. And so look at your units on the right-hand side. We have feet times feet squared, which would get us to feet cubed. So there we go. We've got our correct units kind of matching up there. We have, let's see, 92 feet cubed equals K times, let's see, 12 times 23 gives us 276 feet cubed. Divide both sides by that 276. We are going to get a fraction on here. So that means our K is going to equal, see, 92 divided by 276 equals 0.3, repeating, otherwise known as 1/3. And so if I plug that back into the formula, we've got volume equals 1/3, and I'm going to put the big B in front. And this is exactly the area, or excuse me, the volume formula that we use for pyramids in geometry. So now find the volume of the pyramid with a height of 17 feet and a base with area 27 square feet. So plugging in 1/3, our base area is 27 feet squared. Our height is 17 feet. So multiply those together, 27 times 17. So that's really 1/3 times 459 feet cubed. So 459 divided by 3 gives us 153. So 153 feet cubed is our volume. All right, so today's a little different. You actually have 2 optional practices. So I would do at least one of those, either the check for understanding, which should give you immediate feedback, or you do have some extra practice problems that are posted as well. Scroll down to the bottom of the page for your solutions, but definitely try the problems first. And then you have a graded practice, which actually has 3 attempts on it. So again, as usual, just with any other lesson check, it's going to be whatever your highest score is of all your practice attempts. Let me know if you have any questions.